we are trying to really understand a lot of topics here, right? As you know, starting from climate change, fundamentals, basic science, what's happening around the world, coming to India, and then looking at, yesterday on floods. And we covered the major aspects of what we look for when it comes to floods. But I don't think we are there yet in terms of even doing any flood analysis, because that's not designed to be like this. So we are kind of giving you the topic, introducing the topic, and how to understand the magnitude of the problem, and what are the ways you would address building resilience or making people's livelihoods safe, or how to really understand what's happening with each of these flood events. Those kinds of things you are able to do it. But hands on, for example, looking at how to run a model, how to get the data for making decisions about where it's going to be flooded, how this rainfall is going to impact the landscape. Those things are really the crux of flood modeling, which we are not covering because it needs little more background from you all, as well as time for us to implement those things. But in the interest of time, still we try to do everything possible. Tomorrow afternoon, we will have HMS, hydrologic modeling system, combined with the HEC-RAS little bit, for you to see how the modeling is done. Again, that's only the tip of the iceberg. We need to really understand drought, going in depth by looking at so many other things, like using the data, running the model, trying to understand whether or not we are able to define the topography correctly. It's a lot of work, but at least you are kind of getting there in terms of understanding what it takes to build a full scale flood modeling analysis. Okay, but you may have questions when you go back and see what did I want to bring from this class to do your own work. It needs a jump from this point to reach where you want to reach, but just to optimize everybody's time as well as background, we are kind of going with the introduction of these topics first. The leftover thing I did not cover yesterday was about atmospheric rivers. That's a new concept. It is not new in the western US, but some things are happening here also. So you want to relate to what's happening with respect to climate change. What do we mean by atmospheric river, and what can it bring? We talked about major events, and then talked about climate circulation, MJO, Madden Julian oscillations, to Indian Ocean dipole, IOD, or ENSO, El Nino, La Nina, kind of indices, how they set the stage for bringing large scale circulation, and how can it really add to the existing storms. And three case studies that we looked at from the video gave you some idea. But atmospheric river is one thing, and Hurricane Harvey that hit Houston in 2017 and flooded the whole area is happening in India many times in different forms. I'll just skim through. This is probably about 3 minutes slide. You just watch, how, starting from the forecasting of this hurricane from the sea, when it made landfall, how much of a rain that it got, and where all it flooded, and what was the impact. So just you get a glimpse of this, okay, from Hurricane Harvey. It's a well-developed city, but they did not really, you know, be completely ready for this kind of disaster. So hurricane is forming in the ocean, they're looking at the water vapor clouds, and now Houston is kind of getting hit. The initial forecast was about 10 inches, 15 to 25 inches, that's what they say. And then ultimately they ended up getting up to 40 inches. That's about 1,000 millimeters of rainfall. You can see 30 inches to 40 inches. Big urban area. So we didn't talk about urban flooding. This is the 5-day analysis of rainfall, dumping about 40 inches or 1,000 millimeters, which is not easy to handle. So the forecast was good, and then of course the storm crossed Houston area, and then moved towards east. And 20 inches of rainfall is the effect that you can see here. All the roads are down, everything is flooded, people are suffering. There was a breach of the dam upstream during that time. It started releasing lots of water. You could see the whole area of the landscape getting flooded. Right? So basically, airport, small airport there, one that got flooded. Big ones are also flooded. This is the urban infrastructure, the problem with imperviousness. And of course, people are always excavated, or rehabilitated, moved away from the harm's path. But you can see the damage that it creates and the flow that's coming from different parts, and how they inform the public about the flow from different locations, what are the areas that are impacted, and then they look at how to um, create evacuation routes and take them away from those places, and then shelters they create, blocking the roads, making sure that they are protected. And of course, there is a good level of coordination required from both federal government and then state governments, then local city governments. And then this particular part looks at pre and after, prior to flooding and post flooding of multiple locations. I'm going to actually skip that part because we are not from that area to distinguish between different locations. So I'm going to be actually skipping that. But the part here is, of course, you can see at the neighborhood level how it enters the houses and then makes that watermark that you see here. It's pretty substantial, and we are not new to this. We have seen happening in our own backyard, in our own towns, here also. Houses are damaged. The way how they build houses are also slightly different than what you see here, but the message is people are affected, and 40 inches of rainfall, never heard of, but now, based on our understanding on climate change, increased moisture supply into the atmosphere and dumping that rainfall in a very short span of time. That's what is happening here. It's almost like 2017, right? Roughly about 8-9 years ago, and it is still fresh in lots of people's memory. The other one I wanted to show you is, instead of me talking, I'll just give you an introduction about atmospheric rivers and monsoon when they cross India. Of course, there is a wide swath of moisture transport that happens. In some cases, of course, you see a funnel of moisture, like the river flowing on the ground. You see moisture transport that's happening like a concentrated pipe flow in the atmosphere and bringing lots of rain over a specific area. And this example is from California, which is very well known for atmospheric rivers, and how climate change is augmenting that or increasing the possibility of very strong atmospheric rivers. Okay, I want to just show you that, and then let us see if I am okay to.
Atmospheric river is hitting California less than a week. These storm systems have brought significant amounts of rain, flooding, and mudslides to California. Atmospheric rivers are important for the Western water supply. The National Oceanic and Atmospheric Administration says 30 to 50% of the region's annual precipitation comes from these weather events. But experts also say that climate change could make these storms stronger and more common, supercharging them. CBS News senior national and environmental correspondent Ben Tracy joins us from our Los Angeles bureau. First of all, Ben, so we know rivers are on the ground. When we hear atmospheric rivers in the air, it sounds kind of weird. What is it?
Yeah, so basically these are rivers of water vapor that are pushed by the wind. And we call them rivers because they are long, narrow bands of water vapor in the atmosphere. And when we talk about the size of these things, they can stretch for about 500 miles across and about 2,000 miles long. And when you talk about how much water vapor is in these, it can be up to 20 times the flow of the Mississippi River. So just kind of picture that in the sky, and you get a sense of just how much water is often headed towards the west coast when these things happen. And basically, they slam into the coast, they hit the Sierra Nevada mountains, and all that moisture gets wrung out. And that's when we get images like the ones you're seeing there, all this flooding that's occurred in the last couple of days.
So, Ben, climate change didn't invent atmospheric rivers, but it does change how they act.
Exactly. These are a natural phenomena that have happened. They happen all winter long here in California. And in some ways, they're very beneficial. We get a lot of our moisture, our rain, and our snow from these storm systems. But what's happening with climate change is because the atmosphere is warmer on a warmer planet, there's more moisture in it. It can hold more moisture. So when these storms happen, they can be more intense and they drop more rainfall. And that makes the damage from these storms more devastating.
And what has California done, if anything, to change how they work to deal with atmospheric rivers being worse in the future?
Yeah, I mean, that is an ongoing process because basically the infrastructure in a state like California or Oregon or Washington, where these things often hit, it's built for a climate that doesn't really exist anymore. These storms are getting so much more powerful, more of them are happening, that they really have to reevaluate the infrastructure, everything from, the sewage systems, how this water drains out of cities, where houses are located in terms of flood-prone areas. And then on the flip side of this, how do we capture more of this water when it does happen? We're often talking about drought out here in the West. So when the dry season happens, you need all this moisture. And what is happening now is the planet is warming. More and more of our moisture in the winter is falling as rain instead of snow. So instead of kind of melting gradually over the course of the winter and flowing into reservoirs, we're getting a lot of this stuff all at once in terms of these massive rainstorms. So there are calls to actually build more reservoir storage in a state like California, so we have that water when we need it.
Ben, I didn't mean to bury the lead here, but this is the most interesting part of the interview, that you flew on a plane with scientists over 2 different atmospheric rivers. What was that like? What are they studying and what are they trying to learn?
Yeah, so we just did this. We took off from Honolulu and we flew with these researchers. It was about an 8-hour flight. And they basically fly in the exact same plane that they go hunt hurricanes for during hurricane season. But instead of hunting hurricanes, they are riding an atmospheric river, and they drop these little instruments that have parachutes on them down into these storms, so they can get all sorts of readings about how much moisture, the pressure of this thing. And what they're really trying to do is get a better handle on how intense these systems are going to be when they make landfall, and where are they going to hit. And that's so they can improve the forecast, that can protect lives, it can protect property, and it also can give reservoir operators, we talked about the water storage issue, it can give them more information so they know, do we need to release a bunch of water out of a reservoir to make room for this upcoming storm? Or if it's not going to hit this particular area, do we hold on to this water so we're not wasting it? So they're really trying to get a better handle on that. And they do say that these flights so far have already improved the accuracy of forecasts for atmospheric rivers by 10%. That may not sound like a lot, but that means a whole lot when you're a meteorologist trying to tell people where these things are going to hit.
Yeah, that makes a huge difference. By the way, is this latest river, is it like, what is it done now, or what is it like there in LA now?
No, this is ongoing. I can hear the rain falling right out the window here. It's been going nonstop, basically for the last 48 hours. And we got, I think, about 24 more hours of rain. And some areas are just getting hit with phenomenal amounts of rain. I mean, we're talking upwards of 10 inches, 12 inches in some areas. So, that's kind of like the average rainfall for an entire year in some of these spots that we're getting in the course of a couple of days.
Okay, Ben Tracy, good to see you. Thank you.
Well, actually, that is to give you that is just to give you an idea about the atmospheric rivers, and we may not have those kinds of atmospheric rivers here, maybe in a slightly different format. Instead of concentrated, we may have spread out over the entire west coast of India, possible. So the message here is that we are getting lots of rain, right? And as we see this morning or last evening, we got lots of rain there too, because of the hurricane or tropical cyclone that what we are seeing on the east coast of India. Trying to see how to project my slides here. 1 second. Good. All right. So now we are going to be changing from floods to droughts. We are not changing, the nature is changing, but we need to understand. Anyway, we'll talk about drought basics, what types of droughts that we have, and then drought indices. I also have plenty of literature for you. I'm not expecting you to read all of them today, but by the end of this course, when you carry them with you and read more and relate to what we are discussing here in this class, and then learn more by reading those papers, I think might help. So let's talk about the basics. What is drought? It's typically defined as the below normal precipitation over a specified period. There are a variety of definitions here, so I'm going to go one by one. So it can last for months, it can go up to even several years. California example that we saw for flooding, they also are perennially affected by drought. So that the examples I'll show later. The term people use to define drought is a creeping disaster because it develops slower, you don't even know, and then often unrecognized when it sets up, but then it expands, and the duration, the severity of it gets worse and worse. It can come back to normal depending on the rainfall and the deficit, how much we have and how much is needed to come out of drought. Those kinds of things that we need to understand, which is hard. That's why it's called creeping disaster. And another definition is a period abnormally dry weather with lack of precipitation to cause serious hydrological imbalance. Meaning we don't get rain, we don't get runoff, we don't get recharge, we don't get the flow into the overall system. So that's the problem that we have with soil moisture depletion also significantly. Decrease of water availability in a particular period over a particular area. That's another way of defining drought. And lastly, a condition where the amount of water which has been expected and relied upon for use in any man's activity cannot be met. So there is a supply demand kind of analysis that takes place. But these definitions converge to one thing, right? Basically, we lack water, and India is no exception. We are going to see lack of water. It is difficult to determine the beginning and termination of a drought event. That brings a challenge, and the drought definition can lead to confusion because there are so many definitions. You saw the way how I was defining even 5 or 6 definitions of drought. There is no uniform understanding of drought because it changes from place to place, and also how you define is very important. So that's why it's very difficult. Drought impacts are non-structural hazard and spread over large geographical area. It's not like floods happening in one small city or a concentrated area. But drought, when the rainfall fails, when there is deficit moisture, you are talking about the impact over a large area. So it's very difficult to quantify who is going to be affected more, who is going to be affected less. So that leads to another complexity. And then, of course, human activities can directly impact drought. We will talk a little bit about that anthropogenic drought because we have more and more demands and we are modifying the water budget. So, which is what will create, the demand more and more. Excessive irrigation, over farming, over exploitation of available water, erosion leading to less, percolation or infiltration of this rain water getting harvested and recharging the groundwater. So that's not happening. So it's all becoming adding complications to predicting drought. So now let's talk about drought. I mean, you're all familiar with the term drought, right? But then there are some nuances associated with the way how we define drought. So one is meteorological drought, primarily driven by precipitation, factor. A lack of precipitation below a certain amount, they immediately say there is an onset of meteorological drought. For example, we expect certain amount of rainfall in a month, and if we don't get that, immediately meteorologists say this month we are having below normal precipitation. That means we are setting the stage for meteorological drought. The next one, the big one, is agricultural drought. Basically, we are looking at how the drought is impacting crop yield. And it's commonly associated with other meteorological, hydrological factors, precipitation shortage is number one. Of course, increased potential evapotranspiration leads to depletion of soil moisture in the beginning, but then when there is no repletion of that moisture in the soil column, we are talking about extended drought. And that, when we talk about agricultural drought, it's primarily during the crop growing season, which is anywhere from 3 to 4 months. Unlike meteorological drought, which may be lasting for few days to few weeks to maximum few months. But this one could be going for several months, agricultural drought. Hydrological drought, shortage of surface water supply or flow, and then subsurface water resources in these systems, general hydrological systems. And then there is also depletion in the lake water levels, reservoirs, and stream flows. So generally then we integrate all of this into hydrological drought. Typically it happens on an annual scale because we know when the monsoon comes, the effect of that monsoon remains for the remainder of the year, right? With the flow in the river, recharging that happens, and then crop production and all the other normal functions that we see in the basin happens when you have the full supply of moisture and the precipitation amounts at the beginning of the year. The next drought is socio-economic drought or anthropogenic drought. The influence of drought conditions on the supply and demand of several economic areas and water resources. For example, I talked about water, is a conflicting, entity because the same water is needed for multiple uses. People need it for irrigation, people need it for drinking, people need it for industrial, municipal, commercial water supplies, water demand. And then we are also looking for using that water for energy production, hydropower. And then the last one is, of course, we want certain amount of water to be in the river to keep these aquatic systems alive, aquatic habitats alive. So that competing demand brings in the human element in it. So that's why we call it socio-economic drought. Groundwater drought, that's another one. Drought impacts on groundwater and their performance, primarily when the water table goes down over and over because of over pumping, and then it becomes really a recharge issue, recharge and discharge issues. Basically, we get more water than the water that's being recharged with because of shortage of rainfall. So groundwater drought is a big problem in several countries, including India. I came up with a paper just released 2 or 3 weeks ago on groundwater drought over the whole globe. So India is no exception. So you will find it very interesting. I will share that paper also. Now, let's see, when we talk about drought, it's very amorphous, shapeless, very vague, right? But let me break it down into some simple forms. The run theory that I show here is very helpful to understand three terminologies: severity, intensity, and duration of a drought event. Similar to flood event, if you look at, we talk about intensity or the duration of the storm and the peak flow that we have. In the same way, opposite is the case: severity, intensity, and duration. And then the other factor is when the initiation of drought happens and what is the termination time and what is the drought duration overall. Would be also needed. So when it comes to understanding this severity, duration, and intensity, let me point you to this diagram. The cumulative deficit, this is normal line 0, but then when it runs for several months over a large area, we call that as a severe drought. And then with longer duration, you see here the spread, it could be anywhere from June through December, let's say 6 months instead of 4 months. But the duration is another factor. How long is the duration of this drought exist? It could be years, sometimes 3, 4, 5 years. California had 5 years of drought. And then the threshold, that what we call it here as the negative value, if the intensity or the deeper intensity of drought that we have here, because acute water shortage problems, because groundwater depletion is so rapid, there is absolutely no rainfall, creating high intense drought events. So then you can put them together. So we can talk about the severity or the duration or the intensity of the drought. So you can quantify them. You can quantify these metrics and say how severe, how intense, how long is this drought going to be in my area. This is based on soil moisture, for example, okay? Or it could be based on stream flow. It could be based on precipitation deficit, any variable that we can talk about. But I will come back to the variables and how we will quantify those variables. Okay, what are the variables? Precipitation, temperature, ET, stream flow, soil moisture, groundwater. These are some of the basic indicators that we know already from hydrologic budget analysis. These variables, some of them are measured, some of them are quantified by computer models or estimated by some empirical approaches. Okay, we can get those numbers, get those quantities for a given day, for a given week or a month, for a given location. It could be a watershed, it could be a town, it could be your backyard, whatever it is. Then you can quantify the severity, intensity, duration, initiation, termination, all of those factors for drought. Of course, all of these combinations of variables are used for understanding the current drought and also used for projecting the drought. I will talk a little bit about how we use the projections, climate projections, to quantify drought. Okay, soil moisture is a big variable for drought analysis. Okay, it's a water that's held in the spaces between soil particles, and just an illustration here that what we are talking about is a plant or a tree that exists. Root system is there below, right? And when there is low precipitation, of course, plant is effective in taking that, because they have to have regulation of temperature, like human bodies. Plants also have to regulate the temperature on a daily basis. When the sun comes, when the water is available from precipitation or from the subsurface conditions, they transpire, they perspire like we do to release heat, and that cools down. So this is a very unavoidable or inevitable evil or a function that has to happen on a daily basis for any plant. Okay, now we are talking about how that low precipitation is going to affect the water holding capacity. I think I mentioned this before. This is little more technical for those who are not having this background. Field capacity and wilting point. Field capacity is the upper limit of water that can be held before it drains. Lower limit is wilting point, beyond which the plant cannot extract the moisture. So let's say this is about 40% or 35% or so for a given soil. It changes. This field capacity minus wilting point is the available water holding capacity that can change depending on the type of soil, whether it is sandy soil, clay soil, red soil, or silt, whatever, right? So the amount of moisture that's available in this keeps this plant alive. If the plant shows the sign of stress, that means the moisture that's available in this water holding layer is kind of going through some stress. So we have to put them into ICU for giving them life, meaning we have to irrigate them, or we have to expect more rainfall to come and rescue. Plants are agriculture, farmers, agriculture is, really don't want to see the plants suffering by losing moisture below wilting point, right? So it decreases the yield and the plants die and all that thing that happens. Okay, now we talk about floods and droughts, negative anomalies, drought, positive anomalies, floods again, like we talked about yesterday. I just give you a snapshot view of the whole US here. California, the atmospheric river that I was talking about is in this area, right? So, of course, this area is also perennially low rainfall receiving region, unlike the place that I come from here, which is really mostly greeneries like here with lots of mountains, vegetation, and everything. But what we are seeing here is, historically speaking, more and more rainfall is happening in the eastern part of the country, and less and less on the southwestern side or southern side. This is Texas, which is kind of in the middle. So east is having flooding problems, west is having drought problems. That's a big issue for the US many times. It's not always, but many times. So we try to simulate soil moisture using a model called hydrology model, SWOT or WIC or any other models, and then quantify the drought index and see which area will have more drought and which area will have less drought. And then we quantify or correlate the drought index with precipitation or temperature or stream flow and say which one is the most influencing variable for drought. And again, this is all published. I can share you all the papers. There is so much to be done. All I'm saying is in India, similar approaches are being already carried out by many other institutions. I'm pretty sure when you start to work on drought, you need to understand what has already been done. Okay, so Palmer Drought Severity Index, I will come to the indices later, but this is one commonly available index on a global scale, 2 degree by 2 degree. They calculate Palmer Drought Severity Index. NOAA does it, and then they make it available to the whole world. EPA or NOAA, basically both of them. What I want to convey here, it's not a one-time occurrence, right? It comes and goes. So you can see below zero is drought years. This here, this. Within the last 100 years, if you see many times, 1930s, the dust bowl years, that's what we call in the Midwest. The whole Midwest and US was totally destroyed by drought. That is such a severe drought. Famine, people were suffering, food scarcity, water scarcity, all kinds of problems that they had. Severe problem. Same thing happened in mid 60s, mid 80s, mid 80s also. And I remember some of these events myself, late 80s, 90s, I was witnessing it, but we are not showing anything in the last few years. But 2015 to 2020 was as acute as before. So it's coming once in few years on a regular basis, and it will come not just in the US but in many other places. So we have to come up with kind of an approach to quantify them and look at it from the local scale perspective. How can we quantify drought precisely using all the technology? When they were calculating this, they did not have all the satellite data, models, computer resources, and even institute data. But now we have more and more of that. So our models, our estimations, our maps should be even much better now than before. Okay, so now this is another way of showing US lands under drought conditions. You can clearly see year after year, of course, this is percent of the US land areas. 50% of the land, for example, are at least abnormally dry or moderately drought, almost every year. And exceptional droughts are happening in 5 to 10% of the areas here. Dark red is the exceptional drought. So this code, by the way, the scale D0, D1, D2, D3, D4 are used by US Drought Monitor. I will talk about US Drought Monitor a little later, but now let's come back to the indices. There are many indices, tons of indices, right? But we need to pick the one that suits your needs, that are possible for you to calculate based on the data that you have. Okay, number one, Palmer Drought Severity Index that I talked about. I will also talk a little bit about the mechanics of these indices a bit later. Standardized Precipitation Index (SPI), Modified Palmer Drought Severity Index, Self-Calibrating PDSI, Palmer Hydrological Drought Index, Palmer Z Index, Standardized Precipitation Index for 1, 6, 9, 12, and 24 months forecast, Soil Moisture Based Indices, SMDI, that's what I was mostly focusing in on, and Evapotranspiration Drought Index, ETDI, Standardized Base Flow Index, which is actually related to groundwater, Multivariate Standardized Drought Index, basically more than two variables that we use in a joint distribution function, and come up with a robust approach for calculating drought. Again, this is not all of it. There are many other indices, and I will also give you a handout or the book by some government agency in India. They have listed other additional ones like aridity index and a couple more that I cannot remember now, but that book is a very handy book for you to refer to, for example, to understand how they are calculating. Can you bring some novelty to what they are doing? Okay, so standardized precipitation index is very easy. you have precipitation data for, from IMD or from other sources. You calculate how much of a deviation of precipitation that you have for a given period. It could be day, it could be month, it could be a year, long-term average, and the deviation from that long-term average is your drought condition or deficit conditions. I'll skip for now. So now, basically that is the detail here. You can calculate very easily. You look at this one here, you have deficit conditions of precipitation index below zero for many years in a row for the country like the US. I mean, of course, if you look at how they calculate x minus mu over standard deviation, that is precipitation, actual precipitation for today or this month, minus mean, long-term mean over the standard deviation, right? So this is how they calculate SPI. Just to give you an idea about how precipitation data is used for calculating SPI. PDSI, I talked about PDSI. I think it's an important variable to understand. PDSI is calculated based on soil moisture or moisture anomaly index, they call. This is the important function here, P minus P cap over alpha. This P cap is climatologically appropriate precipitation, CAPP. Okay, climatologically appropriate precipitation is different from actual precipitation that you get. Many times you get, less precipitation than actually what the climatology should bring the rain to the region. Okay, so that means it will actually show the negative values. And then, of course, this alpha is computed based on some of these things like potentiality, recharge, runoff, and loss. We call loss as a generic function here, but you can define loss based on many factors, including soil moisture and actual evapotranspiration. But I will come back to PDSI and modified PDSI because that's one of the important drought indices that people use a lot. Many of my papers actually used PDSI. Palmer hydrological drought index is exactly the same context of drought for the previous month plus the anomaly for the current month. So they calculate this and then use basically the same moisture anomaly, but that CAFEC they call, basically climatologically appropriate for existing conditions. CAFEC, which is a combination of potential ET, which is a loss, runoff, okay, and then rain and recharge and runoff, and then loss here. So the last part is amount of water that's not available to be included in the climatologically appropriate for existing conditions. You will initialize by starting to calculate PDHI just with the anomaly number first. And the first year you can assume for the previous month, for the first time step, you will assume this as 0 and then calculate only the anomaly, and then you increase or calculate for the subsequent time steps from the second time step onwards, right? MPDSI, Modified Palmer Drought Severity Index, there is some minor modification to the original Palmer Drought Severity Index. If you don't follow everything, don't worry, it's not going to stop you thinking about how to calculate. There are models available to do this, but I'm just breaking it down in some simple forms for you to understand. They actually calculate D, which is basically used in the calculation of anomaly here, moisture anomaly that I spoke before. But this K is a function of a lot of loss functions that we use here. Okay, and that K and D is used for calculating the moisture anomaly. So it explicitly considers soil moisture in this case, modified drought severity index, Palmer drought severity index. And of course, we can calibrate certain parameters here to make sure that it's more realistic. If you don't consider soil moisture, many times we overestimate drought, the intensity or severity or duration. If you consider soil moisture, you come to more or less a realistic estimation of soil moisture. So the configuration is like this, basically between PDSI and MPDSI. If I look at, we are talking about potential recharge, which is available water content minus soil moisture, and the potential runoff is basically available soil moisture minus potential recharge. So this is the configuration for PDSI, but then instead of available water content, which is a loose term, people use S max, maximum soil moisture, that is the field capacity, the amount of water that's available at the field capacity level, if you remember the graphic that I showed before. So they use that for calculating potential recharge, and then they also use that for Pmax, which is basically climatologically appropriate precipitation that I was talking about. PRO, or potential runoff, that is calculated. So slight difference between considering available water content versus actual maximum holding capacity of soil moisture for a given soil type. Soil type is very, very important here. So people saw that MPDSI came about to be predicting better than PDSI. So many times people use that version of the model. Now, Z index, again, it's basically a deviation of precipitation from, potentially maximum precipitation that we can get. And then, of course, the adjustment factor that we are talking about here is considering all the losses. So Z index is another widely used. They do this, sorry, I did not mention this before. They do this for every county in the US. For example, each of these boundary that what we are talking about is a county. County is equivalent to our district. You can consider district or slightly bigger than a district. So there are many districts. So by each county, they can calculate all these indices, whether it is SPI, PDSI, MPDSI, or Z index, all of those things. On a daily basis, they do this with the data that's available. It's not complicated to calculate. And these are already calculated and available. People don't even calculate them. So now there is a twist to this kind of analysis. Available data is one thing, but then we need to really understand what are the combination of variables that can help us predict drought better. In that context, MSDI, that is Multivariate Standardized Drought Index, MSDI, is used. In our own group, what we did was a combination of precipitation stream flow, precipitation temperature, precipitation ET, all kinds of combinations we use. We develop joint distribution and then come up with Coppola-based prediction for drought based on multivariate analysis. So that is the kind of approach people are taking nowadays. So I already explained this. So two variables are used, ranking them, come up with this distribution, and then use that approach to calculate using using that to calculate the best distribution that fits probability or the drought occurrence of a given location. There is another term now introduced, like flash floods. Yesterday we saw flash floods in Valencia or flash floods in Texas, and also not flash floods that we saw in Asheville, North Carolina, but it is more or less like a heavy rainfall event. But flash drought has the same connotation or similarity, but which happens in a very short time, and before you realize that we are already in the middle of drought, that kind of a thing, based on 5-day, pentads, they call pentads. Abnormal heat waves or low humidity and strong winds can immediately desiccate the whole area, creating flash droughts. And that's a very big problem right now in many places. You don't have to wait a long time to understand what's happening. If there is some of these things are already there, heat waves and low humidity and strong winds, you should be thinking that, oh, this place might be experiencing flash droughts, anytime. And again, with flash droughts, you have more, because of increased evaporation and rapid soil moisture depletion, maybe making that soil column that I was showing before to deplete very quickly. We did flash drought analysis for the Mekong River Basin, and this paper talks about all this. And what we did was, we looked at climate models. We looked at 2 different hydrological models. We quantified soil moisture from these hydrology models, and then used to project which scenario will have more drought and how often you will have, what kind of severity drought that you'll have, what is the duration that we have. So for India, we remember I showed you in the beginning one paper in 2017 that we did similar approach, but we looked only flash droughts here in this case. So The last one is anthropogenic drought. This is an evolving topic, as you might know. This is a good paper that really introduces this idea of anthropogenic drought, definition, challenges, and opportunities. What it means is that we are not isolated ourselves from the existing watersheds or river basins, right? We are part of the system. We are part of the city like Calicut, for example, in this case. How much water the city requires for running the city on a daily basis? What is the power demand, water supply, that is needed for power production? What is the demand for water for irrigation? All of those human consumptions that what we are talking about should be integrated. And when you integrate, what it means is that the demand will be more than the supply, right? That causes the deficit, the budget part that I was talking about in the beginning. So if you do that, considering the demand and supply, population, as well as land use change for a given urban location, you don't need to call them as any of the other droughts. I'm saying that can be called as anthropogenic induced drought or human induced drought. And that's an evolving topic because we want to understand. The models that I was talking about, some of you may not be familiar, don't even worry. But if you're able to implement any model that can produce soil moisture, get those model outputs, and then understand a little bit about the processes, how they define soil moisture, how they estimate soil moisture, what are the variables they use, how reliable that hydrology model that produces soil moisture, those things that you have to really make clear understanding of. Only then you can use the outputs from there to calculate drought index. So there are two steps here. One is to calculate hydrologic variables or meteorological variables, then use that to calculate all of these indices. And bunch of indices are available for every region, every country, every province, or every state. So we need to really see how we can distinguish the impact of drought, specifically. In some places we are depleting groundwater more than other places. In some places we are having only forests instead of vegetation, irrigation, or agriculture, and things like that. So where the onset of drought and creating, there is a cascade of effect that what we will have to consider when it comes to understanding droughts. I'll talk about that later. But I'm showing here some of these papers. You will see them. Again, I'm showing this, because these are the work, topics for my graduate students, and they did, it's quite dated, like 2018, 19, something like that. But we did both ways, two ways that analysis we did. We did two models, hydrological models always, because we did not trust one model only. But then the other thing is seasonal or short-term forecast versus long-term projections. So when we talk about current conditions, we need to use all the real-time satellite data, real-time meteorological data, come up with forecast. And the other approach is using some of these already available global forecast system products, GFS. Okay, that is actually helping us to understand, will we have drought in the next few months? Will we have drought for the next growing season? Something like so. It accommodates some of these climate anomalies into picture, and it comes up with realistic assumptions of precipitation temperature. Although I say realistic, but precipitation is questionable than other variables. Nobody can predict or do a good job of telling what will be the precipitation 9 months from now. That is a challenge. Forecasting precipitation is a challenge. If you cannot get good precipitation data, drought analysis is useless. You have to keep that in mind. Good precipitation data is very, very, very important for doing right analysis of drought. And then we combined different variables and looked at how it's happening. So the same graphics that I was showing, we developed this, and then this drought monitor that I will talk about is used as a standard, what do you call, some kind of a proxy for actual drought data. We don't have drought. How do you have data for drought? You have to have a spatial map based on certain functions, certain deficit variables like precipitation or stream flow or decreasing groundwater level and whatnot. So USDM has done a good job of compiling all of them, combining all of them, and coming up with a map that shows reasonably accurate condition of drought condition for the US. They release this data on a weekly basis. We use them for validating the models, validating all of the approaches that we do. Okay, so for India, probably you remember I showed this before, the same approach. This is on our long-term projections. Two terminologies that you will have to distinguish, right? When I'm talking about drought forecasting and drought projections. You know the difference between those two, right? What is the difference? Drought forecast. What do I mean by that? Anybody? Speak up, please. I cannot hear because of all the fans. Forecast means it's basically on a short time scale, 3, 4, 6, 9 months. Projections are over a longer time period, like climate change projections, right? Temperature for the next 70 years, precipitation projections for the next 100 years. So likewise, so what we are talking about here is projections of future drought. Based on that, we calculated two quantities of drought metrics. As you know now, duration. When does the onset of drought occur and when it ends? That's the duration. And then how often you see that? That's the occurrence part. So we quantified them on that first day. I think I showed. Now I'm explaining this. So this is basically your month on x-axis. 4 months. Many places in the country will have at least 4 months of drought in the future because of increased temperature, lack of whatever storage facilities. I would not say lack of precipitation because we are going to have more precipitation in this country, right? But then occurrence. How many occurrences of drought, of whatever occurrence. I mean, when I'm saying occurrence, it could be meteorological drought, right? Short term, short spell, few days of drought that happens, but again it goes away. How many times like that in a year that you have? 5 times, 10 times, 15 times? That's the count that I have. That's called the occurrence. And hydrological drought, for example, in a year or in multiple years, how many times that I have? Measure the flow in the river, whether it's Periyar or Kaveri or Ganges, and then look at, oh, this year it's below average. So I call it a drought year based on hydrological index. But then if that is the same type of situation that we see year after year after year, how many times we have in the next 50 years or 100 years? That's how I count. That's the count occurrence part that I'm talking about here, okay? I think I talked a little bit about it before, multivariate drought index. Again, one thing I want to stress here, people come up with new index. You can also come up with one. If you want to have a name associated with that, and if you come up with a drought index, put your name on it and people will call. It could be, Priyank's index, or it could be Sharma's index, or whatever, You have to see the innovation of what is needed to fulfill the demand of our understanding drought for a given location. Here, another index that I'm talking about, Joint Drought Index, JDI, was proposed using accumulated precipitation and stream flow to monitor drought conditions. So what they thought was existing droughts indices are not useful. So now they wanted to combine both. So they call it JDI. Some places they call MSDI that I introduced already, multivariate standardized drought index. Then they use copula function. Once they get the joint distribution, they fit the curve, fit the distribution using copula functions, and then they call another name for that. Basically you can call with anything you want, but all I'm saying is what variables for a given location that you are looking at is needed for understanding drought. That part you need to be clear about. Okay. So this is, marginal, you'll fit the marginal distribution, you take the, right copula, multiple copula functions are available. These are built in library in MATLAB or other places. Come up with a joint distribution. That's more stable, more reliable, more trustworthy. That's what we found out from our analysis. In this paper, if anybody wants to read and understand, Madhu Sanka Tilakaratna, actually he did that work back in 17. But It's a well cited paper, gives you idea about how we did the drought. The next work we did was looking at relating drought to food production, right? So that's an important part we need to understand. We talk about drought relating to drinking water supplies, to irrigation, whatnot, everything matters. But food security is the dimension that people are thinking of right now. What we did was we tried to calculate um, drought index, and then we looked at the crop yield and then tried to distinguish between non-drought versus drought year and how much of a difference in the crop yield that we have, loss of crop yield. And then we converted that into inverse of bringing more area for agriculture or adding more water for not losing the crop for a given season. So we tried to flip the question by saying, I don't want to see a loss in my yield, how much more water I should apply or how much more area that I should grow. That way, as a farmer, I would not find it a loss for me even during the drought years. So we tried to kind of ask that question and came up with countrywide analysis by this paper, which is very useful for you to refer to. And we came up with this, there are 4 countries in this map. This is lower Mekong region. Thailand, Cambodia a little bit, Laos, and then Vietnam here. So by province and by different climate models, we looked at what is the yield difference that we have because of drought. And then we kind of converted that into more areas that should be brought for irrigation. That way you will not be having a problem of crop yield loss, and food security will be not at stake. That is the kind of answer that we came up with. I talked a little bit about US drought monitor before. They use bunch of index or indices, PDSI, SPI, Keach and Byram drought index, model soil moisture, 7-day anomaly of stream flow, precipitation anomaly, all of those combinations, and then they come up with a weekly map for the whole country. This is done in Nebraska. I have witnessed how they did it in my time when I was there. The map is produced every week. This is a little bit of out of date, but you can find out even for today or this week what was the drought condition in the entire country. I think India needs like this, a map. Probably it already exists from some other groups, but more and more of these kinds of products will be of use. They use, of course, different government agencies are providing support to come up with these climate indices, drought index, and then local reports from 350 experts. They congregate, they collect all this information. Coming up with a map like this is not easy for a country like US. It is 3 times bigger than India, 3 times smaller population wise, but still they have to really make sure that the information is available for everybody, scientifically validated, a good reliable source, and people trust this data product. And I have used it, I showed you before, and you might be able to get similar product in India also. So they classify drought with 4 or 5 indices here, categories D0 to D4, abnormally dry with certain ranges. Of course, exceptional drought will be really too deep, that is -2 and below. Okay, and again, US drought is used as the proxy for drought validation in many studies. Again, there are other indices that are available that I'm going to see my clock here. I have 15 minutes. I need to show you some videos before we end the class with another guest speaker that we have right after me. So you understand the concept, right? People come up with a combination of variables to quantify certain index and call it by that name: soil moisture index, surface water supply index, or combination of evapotranspiration. All of those things that are shown here. Again, some of these notes you can read them later. Groundwater drought is an important part that you need to understand, because it's a slow, when we talk about drought, that itself is a creeping disaster. But groundwater is even more creepier, because we don't even know how much are we pumping, how much is available. It's like a black box. People keep pumping. People put more and more, powerful pumps, when they can go drill deeper and deeper and deeper. But when they go to a certain level beyond that balancing part. I mean, ideally, what should happen if the water table should not drop below a certain level? Your pumping should be equivalent to how much you put back in as recharge. Discharge should be in balance with recharge, right? Discharge should be in balance with the recharge. If it does not happen, if there is that balance that is broken, 1 year you will see a drop, second year you will see a drop. You will not even realize your pump will work and you will have free electricity or more, money to buy electricity to pump more, and then you go deeper and deeper, and then you find out water is not coming, and then replace that motor with another one, deeper one. That's what people do now. They go deeper and deeper and deeper, not knowing that these water in aquifers are collected over hundreds and thousands of years that are being depleted in such a short span of 50 years or less than 50 years. We are seeing that. We are witnessing in many regions in India, whether it's Andhra Pradesh, Telangana, Punjab, Haryana, maybe Karnataka and Maharashtra to some extent. All of these places are exploiting groundwater unsustainably. So as a water manager, as a civil engineer or a groundwater specialist, if somebody wants to look at it from that perspective, what is the balance? What is the budget? What is the groundwater level drop that we are seeing? There are studies. We have done some work on it. Refer to some of the papers. By the way, I just wanted to let you know, all these papers are also trackable through Google Scholar if you want to search. If not, just let me know. I'll give the contact information later on by the end of the day, by the end of the course. Contact me if you need those papers, for your reading. I'm skipping some of these slides because they're repeats of what I showed before. I think the message I wanted to give you here is that future scarcity of water is certain. And several studies have shown that. And of course, we are talking about future in the sense, in the context of climate change, right? So all I'm going to show here is this, 4 or 5 different types of combinations. You don't know which model is good or which model is bad. Climate models, when you're taking precipitation or other variables from them to calculate, you don't know what they are. So we normally do this analysis. Change in precipitation, change in temperature, X and Y axis for different models. And then, for example, I call this as wet and cool. What do I mean by that? This model produces more rainfall, 15% more rainfall, and temperature is also not that high. So I would call this model as wet and hot model, right? And this model is really a dry model with cool temperature, cool conditions. So I want to kind of use all kinds of combination of different climate models to use for my analysis. For drought particularly, you need hot and dry models because they are the ones that will give. But you can also use the wet models as the baseline model, and how much of a range that you'll have. You can bracket the uncertainties by doing all model analysis. But if you don't have time, if you don't have resources, you can do a similar analysis and find the best model that will serve the purpose. Okay. Again, I think I'm repeating some of these slides here, so we can skip that. But it's not easy to get the data, right? Yesterday, we had a lecture on satellite data, right? I think you got plenty of idea listening to that lecture. I also had this, so I thought I will share this. I also put the links for the data, whether it is remotely sensed precipitation. One of the primary variables for hydrology and hydrological analysis. TRIM is the one, TMPA or GPM, Persian. These are the data. Where to access this data, I have put them over here. What you have to do, of course, collect the data first. Look at holistically how, to make sense out of that. Remote sensing based precipitation is not bad. It is not the same as your in situ station based precipitation, but definitely a good alternative. Same way, remote sensed ET is also available. So if you can calculate using certain models, LST based or NDVI based, energy balance based models, you can come up with ET maps, can come up with remotely sensed soil moisture data, active and passive. I give the distribution, or the sites where you can get the data for the period that we can get. All I'm trying to say here is that these products are providing the baseline estimation of some of those hydrological variables that we are talking about. The last one is groundwater. GRACE is widely used. Some of you might have seen this already from 2002 onwards. They have used this. All they do, I mean, I'm not going into the details about the satellite product. You can read by yourself. But this particular one is really fancy. The idea is that when they pump more water, the earth rotation is changing, or the tilt is more or less. So that minute difference they are able to see through the satellite, and they calculate the change in water storage, how much is pumped, how much is lost from the water storage below the surface, is the one they measure through the satellite, and that is used in groundwater drought analysis, which we have used at least half a dozen papers, 6 papers or so, that we have published using groundwater data. So look at those papers if you are thinking of expanding or furthering those kind of analysis. And I will show you this small video before I stop for now. 2 videos, but I think let me start with one. It's a very short video, 2 minutes, so pay attention to every detail.
Drought is a defining feature of Australia. Its impacts can be distressing and affect the whole community. But not all droughts are the same. They can vary in the size of the area affected, the intensity, and how long they last. So what do we mean by drought? There are several types of drought. Meteorological drought relates directly to less rain than usual. Australia's rainfall is highly variable. When somewhere receives less rain than usual, we say it has a rainfall deficiency. If there is much less rain than usual, we might talk of serious or even severe rainfall deficiencies. Continued low rainfall can mean less runoff and lead to hydrological drought, especially when combined with high temperatures. River levels fall, water storages drop, and soils become drier. This lack of water can go on to affect people and their livelihoods. Agricultural drought means reduced productivity, lost income, and a strain on those communities. Socioeconomic drought sees effects spreading through the wider community. In fact, our whole environment is vulnerable during drought. It's not easy to say when a drought is over, or even how much rainfall is needed. There may be enough rain at the right time of year to grow a crop, but not enough to replenish water storages. In some cases, it could take many wet months for the landscape, waterways, and communities to recover. Once the environment and the community have enough water to meet their needs, we can consider the drought to be over. And with Australia's changing climate, some parts of the country are expected to spend more time in drought. Alongside warmer temperatures, these droughts may be more intense. Use our website to find out about drought in your area.
This is
Drought.
This is from Australia, right? The example is from Australia, but it applies to us. I think the concepts that I was talking about before is exactly the same, different types of droughts and how it impacts. So again, I think we talked about it before, but I will emphasize on this, which is understanding drought. What it means is that we are talking about the impact, right? Impact driven by climate variability or impact driven by climate change, all of those things, right? But what are we going to do about it after we identify that my region is impacted by drought? I mean, impact analysis is only one part of it. Now, the next part of water management or building better environment or future, better future, is to find the alternatives, right? So I'm going to show in that spirit of another small, I'll clip only the portion that are really needed for us, which might be of use, because many Indian cities are going to have problems of drought, right? So what are we going to do about this is given by the down-to-earth Sunita Narayan very effectively. Instead of me repeating it, I thought I will just play only few clips because we are also waiting for the next speaker. I thought of using this time just to give you maybe 5-7 minutes of the entire 15 minutes video. We will not watch the whole thing, okay? I just wanted to show you that. Like floods, what we saw before, drought is going to be a big problem for India. So it's all in your hands to understand the characteristics of drought and inform.
Day zero, when you run out of water. A few months ago, we were all talking about a city in India called Bengaluru, which was desperately in need for drinking water. Today in Delhi, we have a water crisis. The water crisis is across our cities. Often it is hidden because it is not talked about. It is in the form of huge distress of people having to depend on tanker water, on groundwater, on any source of water for their drinking. So the crisis of water is linked in many ways to the crisis of climate change. It is linked to the heat that we are seeing in our cities, but it is also linked to the fact that we will see a changing rainfall pattern. We are already beginning to see that we get more rain in fewer number of rainy days. Remember, a country like India, we get rain on an average in only 100 hours in a year. Out of that 3,700 something hours, you get rain on an average in 100 hours. Now, because of climate change, you will get more extreme rain events, which means more rain in fewer number of rainy days, rainy hours. If you look at the data from across India, you will find that many weather stations are already reporting that they are breaking the record of 24-hour rainfall, which means that a city, a region, can get its annual rain, as much as a whole year's rain, in a matter of a few days or even one day. So this is what is beginning to happen. We first cry because we do not have water, then we cry because we are flooded. This is the cycle that we are beginning to see is to everyone. And this shows up in the fact that most of our cities today are dependent on groundwater. It's not official, so nobody will tell you that this is what is happening, but that's the reality. When you hear about the tanker mafia in a city, please remember that the tanker mafia in most cases is bringing its water from groundwater. Wherever the water supply does not reach, people have no option but to either dig a well or to phone up and get someone to supply water to them. Now, this is really what is happening city after city to our water supply. Link it now. Think about the second link to this, which is sewage. When you flush, and every time we flush, please remember one fact. 80% of the water that comes to you leaves. So if you get 100%, 80% of that water leaves your house as sewage, 80% of it. Now, I just spoke about the fact that our water boards do not have money to even supply water. They do not have the money to take back that sewage, to build underground sewerage, to pump it to a sewage treatment plant, to treat it, and then to dispose it in our rivers. Now, this is why our rivers, our lakes today are nothing more than sewage canals. This is why today we have a double challenge of clean water on one hand and dirty rivers on the other hand. Now, even cities, and there are rich cities, Bengaluru, for instance, has invested in building and upgrading its sewage treatment capacities. Delhi has done the same. Today, Bengaluru has almost the ability to treat 100% of the water that it supplies and that it gets back as sewage. But now this does mean that we need to make sure that the groundwater becomes part of the official water system. That we supply, that the boards, the water supply boards, look at groundwater as an official supply source. They look at bringing water long distances only when their local water systems are to have a deficit in a particularly bad drought here. Otherwise, or if there is a shortage. Otherwise, you really look at groundwater and rainwater as your main supply system. It will also reduce costs. It will reduce your distribution losses. It will make sure that you are being able to mitigate the flood that is going to happen in our cities. Now, this then gets connected to the sewerage system. Today, again, our sewerage systems mean that we want to transport sewage underground to longer and longer distances and then treat it and put it back into the same river. Now, suppose we were to think about what CSE keeps talking about, what we keep talking about, which is fecal sludge management, which is that you take on-site systems, you take the fecal sludge from there, and that you take it to a neighboring, through a truck, a tanker, you take it for treatment, and then the treated water is reused, recycled, and the untreated water, the sewage, the septage, is put back on land. So you close the nitrogen cycle as well. You also think about recycling every drop of sewage. And you can do that also using the same sponges of your cities, the water bodies, so that that treated sewage can go back into the water body and can again get recharged into the groundwater. It's kind of thinking about the city as a closed loop, the water system of a city as a closed loop. It's about rethinking and reconnecting all of us to both the rain that falls so that we mitigate the floods, to the fact that we will not want to pollute our groundwater, to the fact that we will have sewage which is treated and available as reuse. So there is an
opportunity. That's what she says. So I want to end there. I wanted to say this. I mean, impact assessment is very much needed for good management, better management, best management. But then, how do we come up with solutions? So this part of the, solution that I'm going to be also talking about later on when it comes to building adaptation measures, building resilience. How do we really assess the current condition? How do we build infrastructure that are going to be facing the future, stress, future, hydrologic shocks? And then how can we really adapt, again, reassess and readapt? It's a loop, it's a cycle that we need to be thinking constantly. We cannot just think only about the, extremes in an isolation, saying that how much flood are we going to have? How much drought are we going to have? That's the impact assessment part. A lot of studies have already happened. A lot of studies are already happening. So your job is to even do that same thing or improved version of that, but then link it up to the next level of looking at measures for managing the adverse conditions. That's what I would suggest, whether it's flood management or drought management. So that's the thing that you should take away from here. I'm going to stop here for any questions. Do we have anything to discuss here? Do we have the next speaker already? Hi. Okay, so let's then stop here. If you have questions, save it for future. We can come back and discuss. Tomorrow we will have related topic. When we talk about drought, heat is also there. So we need to talk about that. Then, when it comes to excessive precipitation, mountainous terrain like Kerala, we have witnessed landslides. I will show you some examples from the place I come from, but then we have also seen yesterday in one of those videos of landslides. So we'll talk a little bit about landslides, but then I'll show some of my own work, vulnerability mapping of landslides for Kunnur, Nilgiris area, and then we will finish with urban heat island discussions by tomorrow. So I will stop here now, and then we will invite our speaker who will talk about drought analysis. Sure. Okay. So we will have a 5-minute tea break now and then reassemble. So it's 10:40 now. So let's come back here by 10:45. 10:45. That's it. Thanks.